Finding a basis can be a very interesting problem to approach. Here, I think it is very interesting. So we're in a casual three-dimensional space, and we have, you don't need to identify this, but we have an equation of the plane. It's two-dimensional. This probably hints at the fact that we will need two linearly independent vectors to span two-dimensional plane. You need two linearly independent vectors. And I can reach any point on the plane just by adding and scaling these two vectors. So this at least should be the, I don't want to say intuitive, but the nice visual image that you should think about when I say we have a plane which is two-dimensional, then we'll probably need two linearly independent vectors. Linearly independent in the sense that they add to the span of these two vectors. It's not another vector which, let's say, lies on top of it, then it is practically useless because it's not really adding anything. You're still locked in here. Even if you stretch, even if you add, don't unlock a new, let's say, dimension like you would if you were to add these two vectors. Also do like, I hope at least by pen waving and that it is clear when I do these gestures. Okay, so we need two basis vectors. They need to be linearly independent. Well, let's just choose any two vectors that satisfy this equation. This can be pretty easy, I would say. Maybe I'm wrong, but let's say I take y to be equal to 0, because why not? Just an example. Just plug in y is equal to 0. Then what is a suitable choice for x and z? Well, there is an infinite class of things that should be suitable. But what's the first one that pops up? Yeah, I think this is in minus, this is in plus. Then I should probably choose x to be 5 and z to be 7. Then I get 7 times 5 minus 5 times 7. And I play the same game. So let's say I make x is equal to 0. Same equation. Then what should my y and z be in this specific case? So these are two different cases. We need to, of course, distinguish that. Then it should be clear that you should choose y to be 5 and z to be 2. Then you have two vectors. So the first vector that arises, an example of a vector that satisfies this equation and lies in this vector space, is the vector, well, we chose y to be 0, chose x to be 5, and z to be 7. And we also have another vector, which is x is equal to 0, y is equal to 5, and z is equal to 2. So these are two vectors. They should form a basis if they're linearly independent. Naively, you could say that you can't really multiply this vector by a constant in order to get the other vector. So they look linearly independent. And let me tell you this, they are linearly independent. If you would like to end the video here, then you can 100% feel free to do so. But I would like to take this one step further. But this is just for me, just for because I'm a bit paranoid when it comes to linearly independent vectors. So I need to double check this, and I'll try to do it quickly. So these two vectors are linearly independent if this very specific statement is true is about them. I won't write the full formal rigorous definition, but I'll just give an example. So let's say this is the purple one, this is the blue one. If there is a scaling which I scale alpha 1, if I scale the purple vector by, and another scaling which I scale the blue vector by, and I get to the 0 vector, then the only way I would get to the 0 vector is if my first scaling shrunk to 0 and my second scaling shrunk to 0. Let me make this more precise. So the only way I can add and scale these vectors to get a 0 is by shrinking this all the way to 0 and shrinking that all the way to 0. So this way I would reach my 0 vector here. This is simply just saying that these two vectors will not cancel each other out. An example of two vectors which will cancel each other out are two vectors on the same line. And these are two linearly dependent vectors. This is a pair of linearly independent vectors. So I'm just trying to motivate the definition at least. So let's assume that if there is a scaling which I can scale first vector by and the second vector by, well, separately, to get 0. 0 in the sense of the 0 vector. That's why I put this here. And what I'm going to do now is I'm going to distribute. So this will give me 5 alpha 1, 0, 7 alpha 1 plus 0, 5 alpha 2, and 2 alpha 2. And I can add these two vectors. Well, this is going to be 5 alpha 2, it's going to be 5 alpha 1, it's going to be 7 alpha 1 plus 2 alpha 2. Guess what? If 5 alpha 1 is equal to 0, this means that alpha 1 should be equal to 0. And if 5 alpha 2 is equal to 0, then this means that alpha 2 should be equal to 0. So what we've effectively just did right now is we formally and rigorously and mathematically checked that these two vectors are actually linearly independent, because the only way you can combine them to get the 0 vector is if the scalings are 0. In other words, these two vectors will never cancel each other out, like we saw with this specific example. So this is something that does not happen. And so we have two linearly independent vectors, which means that they will probably add to the span, and we can use these two vectors to reach every single point in our very specific and very nice